And the session of this morning will be focused in particular on GW, so the calculation of quasi-particle corrections within the GW scheme. And we will have 3 theoretical talks on the topic. The first one by Andrea Marini, who is the main developer of the Yambo Code and actually founder. And then there will be 2 more talks from Alberto Guandalini and I don't remember from Davio, what's his name? Okay. Okay, so please, Andrea.
Yes, so let me see if it works. Yes. Okay. Okay, so good morning, everybody. So the first talk of this morning will be about GW. So we enter in the real business. And so the lecture will be pretty long, but we go step by step rather than, flooding you with the questions and so on and so forth. So the GW, I will introduce the GW in 3 ways, 3 different ways. And the first will be an heuristic GW that is very much based on Hartree-Fock. So what you need is just Hartree-Fock plus an intuition of what you need to go further. And this will be the less mathematically formal derivation. Then we will move to the actual equation of motion, and there we will actually see a way to produce equation of motions that is general. It does not only apply to GW, but given an Hamiltonian written in terms of some fields, you can get an equation of motion by this technique. Very simple, not very complicated. And then we will understand mathematically GW, where does it come from? At that point, we will split our analysis in a diagrammatic approach and in a functional derivative approach. So 3 different ways to see the same problem. This is essential for you, also as it is for me, because it gives me different ways to derive the same stuff. Having different perspectives also gives you an idea of the limitations of this method, because you see it appearing as the result of approximations that apparently they are different, but they're just different ways to see the same approximation. Okay, then. What is the main problem we need to solve? Because, from a very elemental physical point of view, the problem is very clear and very simple. So you have this many-body problem, this many-body Hamiltonian, and the many-body Hamiltonian is complicated because you have the 1 over r prime. So if you have a charge at r, then another charge at r prime, there will be an interaction between those 2 charges, and this interaction is long range. So this is the problem. So you can imagine that everything would be simple if you remove this interaction and you describe your system as 2 independent particles. This would be just simple, because even simple intuition will tell you that the dynamics will be the dynamics of the 2 independent particles. But the problem is the interaction. So now you may wonder, if I have a system of 2 bodies or many bodies interacting, what happens if I remove one of the 2? If I try to get it out? Or alternatively, if I try to get it down, to get it in? In the first case, this is just for the mission. Yesterday we had a talk by the experimentalist, was exactly explaining from the experimental point of view what they see when the electron is removed from the system. In general, experimentally, if you look at the distribution in energy of those photo-ejected electrons, you see they are not centered at a single energy. In general, when you do ARPAs, you see structures. So this is, I don't know, photo emission as a function of the energy. So you don't have a delta function, because if you had a delta function, then you would say, oh, they are not interacting, I'm just removing one electron. But instead, you see structures. This is because when you do phone emission, you are actually accessing the excited state of the material connected to the states with different number of particles. Now, let's forget for a moment the problem of the super complicated many-body problem. Let's do a step back. And we take the problem from a completely different perspective. If you have a system and then you add a charge and then you assume that this charge is tiny enough to be treated within perturbation theory, the question is, how can you calculate the change in the global density of the system? So now the problem is completely different. We are talking about a single charge that is added to your system, and this charge is assumed to be a tiny perturbation of the entire system. In this case, you can actually use the so-called Kubo expression. Ryogo Kubo, that was a Japanese theoretician, derived the exact expression within linear response for the change in any observable upon application of a tiny perturbation. In this case, our perturbation is this additional charge. So in the case of Kubo, the problem is written explicitly in terms of an external potential. We will see in a minute what is this external potential. For the moment, let's just concentrate on this simple problem. So you have the Hamiltonian, that is the bare Hamiltonian that can be as complicated as you like. You add a tiny perturbation, and then you just apply perturbation theory on a certain observable. In our case, the observable is just the time-dependent density. So rho is the density operator, and we calculate the time-dependent density of this total Hamiltonian, assuming that the external perturbation is weak. This is Kubo, and is the basis of linear response. It's the same expression that you apply to get absorption. Exactly the same. I think that yesterday David mentioned it. So the point is that now the external potential is not the external electromagnetic field, but it is the potential connected somehow to an additional charge. Okay, then if you do the math, it's very simple. You can realize that the induced density, that is the density that is induced by this perturbation, is proportional to the external stimulus with the proportionality given by the density-density response function. The density-density response function is defined here at the end of the slide. It's just a mathematical object. It's the average of the commutator T-ordered, causal, not T-ordered. And actually, this is just describing a very simple physical concept. Within linear response and Kubo, if you apply the perturbation at T, anything happening will be at later times. I mean, it's just simple intuition. Okay, so then the key point is that this induced density will be proportional to the external density with the response function. So you see that we made appearing the response function by following a completely different path. But we have the response function. The response function is the main actor in GW. So you will see it appearing in any form. Whatever path we will take to GW, at a certain point we will have to introduce the response function. So now, if the induced potential is like this, then we may wonder, okay, but if I add a charge and then the system produces a change in the density, then I can calculate easily at least the back effect of this charge to the entire system through the solution of Poisson equation. You know very well that in electrostatics, a charge produces a classical potential, and this classical potential is solution of Poisson. And the solution of Poisson is just the convolution of the induced charge, in this case, with the column potential. So this is the induced potential that appears in the system upon addition of this charge. So now we have to do a step forward and say, okay, if I want to describe the effect of the potential in the whole dynamics, I have just to amend my total Hamiltonian with an additional Hamiltonian that, in addition to the external potential, includes the induced potential. Now, if you do simple math, you realize that this new potential, this new piece that you add to the Hamiltonian, has the form of a density-density interaction mediated by this object, V chi V. We made it appearing without using any diagrams and whatever. Just intuition and electric theory. Now, if you do this, you say, oh, but this means that the perturbation made appearing in the Hamiltonian of a term where two densities, that is the external densities, the external charges that I've added, actually are not interacting through V. So this interaction that is V, you see, this is V. Now, if you do the dialectic approach, and then you consider that so you have just to review this picture. Imagine that now the blackboard is completely empty, and then I add one charge. That's fine. There are no other charges. I'm in a vacuum. But then I add another charge. And then my heuristic derivation demonstrated that those two charges will now interact through something different, because all the other electrons will react to the addition of the charge. So you realize quickly that this interaction here is not V, but it's W. That is proportional to V chi V. So by using this simple argument, you should have understood that the lowest process we may imagine in an external material, where actually there are collective reactions, is to replace the long-range interaction with something different, this screening interaction. This screening interaction is just the interaction that takes into account the reaction of all electrons to the perturbation. This very heuristic approach is actually the basis of even more complex theories. If you try to look inside the Landau theory of quasi-particles, it's very much based on the assumption, on the idea, on the picture that the particles at the lowest order, they can be considered as dressed and interacting through a potential that is different from the bare potential. And you can really build up lots of physics on this simple picture. Of course, now we have the problem of building up theory on top of this simple picture. For the GW, we have not all the huge problems that Landau had, but we can use a simple intuitive link. Because you know, because you have derived in a completely different way, that the lowest and most simple approximation to the many-body problem is Hartree-Fock. This is something that we study in our university courses. And Hartree-Fock can be also derived without using complex many-body things with the variational approach. So the Hartree-Fock can be introduced in many-body at the same way you do with DFT. You may ask, what is the lowest energy state that corresponds to a Slater determinant? And this lowest energy state is the one solution where the orbitals are solution of the Hartree-Fock equation. So of course, this is something you have to know. In Hartree-Fock, you actually get two potentials. One is the Hartree, is the classical potential. And this is very much similar to what we had derived before. In the Hartree-Fock approximation, the Hartree potential that is an object that is present even in the exact theory, is there, period. It's just saying that at the lowest order, if you add a charge, there will be an electrostatic potential. This is Hartree. But then you have an additional piece that is Fock. The Fock term is purely quantistic. and it's due to the antisymmetric properties of the Slater determinant. This is because the wave function electrons are antisymmetric. Because of this consequence, because of this, actually you have the consequence that two electrons cannot sit in the same state because of Pauli exclusion principle, and this actually induces an additional piece that is the Fock term. Now, the Fock term, the difference with the Archie term is very simple actually, it's very tiny, even if intrinsically they are very physically different. But from a mathematical point of view, the Archie potential is a density. There is a density up here. You see x prime, x prime. In Fock, instead, there is x, x prime, but still mediated by the Baire-Coulomb interaction. Well, now, my intuitive, my heuristic derivation says that, okay, this screening is a quantistic process because it's not present in the classical theory. Then I can amend the quantistic part of Archie-Fock by replacing B with W. I mean, guys, this is GW. It's exactly GW. GW is a screened Fock potential. It's not more than this. Then, okay, there are complications due to the frequency dependent. We will discuss. You will see it at length. And there will be even lectures about this. But from a very conceptual point of view, if you have to explain the GW to a student that knows nothing about diagrams and blah, 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 you can use this approach. Now, this approach, even if it is very simple and not at all formally derived, it actually leads to an important observation. You can find written in the literature that the GW is a dielectric approach. Why is it said to be dielectric approach? Because it assumes that the main physical process that occurs in a many-body system upon additional removal of an electron is the screening of the interaction. So is a response function. This is the key. So the response function is the most important and dominant process that occurs in your system. And this is dielectrics, because the response function that appears in GW is exactly the same that gives absorption. So with the same object, the response function, you can calculate the screen interaction and also the absorption. But the absorption is an object of the dielectric theory of solids. This is an important concept that you have to keep in mind. Even if you do then formal derivation, we will do some formal derivation in the following. But this is actually the main conceptual content of the GW approximation. Okay, now let's see. Of course, what is the pro of this derivation is that it is simple. You get it done in a few slides. What is the cons? The cons is that it is not formally derived. So I don't know under which approximation it has been derived, and I cannot judge the validity of the theory. This is very essential for you. Whatever theory you are going to use in your career, it is very important that you know it at the level of understanding under which limitations you can use the theory. I mean, there are some rules. You cannot use the theory for everything. And now, let's see what is in the case of the GW, because we do now a step forward. And we use a more formal derivation that will be common in the first part to the diagrammatic and to the functional derivative approach. So we keep in mind, again, it is important that you keep in mind your heuristic derivation, because that's the physical content. This is at the end, the physical message of your derivation. But then you have to find a way to derive it more clearly. So we can revise quickly the concept of many-body. Okay, one important thing is many-body is that if you don't remember it, you need to review it, is the second quantization. So whatever root many-body has to go through second quantization. So the transition between the wave function representation to the quantum field operators. This is something that if you don't remember, please review it. But in general, it's like chapter 1 of any book about many-body. Any book about many-body, chapter 1 has second quantization or review. So it's simple. the important thing is that this object, this electron, will be described as the state of a quantum field. So this hat is just to specify that it is an operator. So this object has anti-commutation or commutation rules and can define propagators, is an operator. So actually an operator in the Fock space of the states of electrons. So if you don't remember this, the things just you have to revise. But once you know that the electrons are described in terms of field operators, then you can actually draw a parallel with this life of an electron hole, an electron moving. So you have your ground state system, and then you add. So this psi dagger is really the addition at point R, is exactly what I draw on the blackboard, at point R of an electron. Okay? And then the many-body now will tell you, yes, but how is this original particle at R moving in time? And this is through the time-dependent time evolution operator, this U. Thus this U is describing the evolution of the electron from time t, when it was added to the system, to time t prime. And then when you are at time t prime, you can project. You can project by annihilating the electron. So psi will annihilate. Psi dagger will create, psi will annihilate. So this is second quantization. Just trust me. So once you have calculated this process, you can actually define a transition probability. So you can say, what is the probability that when I add an electron in a point, I will find it at point r prime and t prime? Many-body and quantum physics is statistical theory. So you describe everything in terms of probabilities. When you connect to the experiment, you define everything in terms of probabilities. And another important thing that makes things a little bit complicated, and this is something, I don't know if you read the quote, I think it was of Freeman-Dyson, of the conjecture of Feynman of rewriting quantum physics in terms of trajectories. And Freeman-Dyson was saying, I mean, this guy is completely crazy. You cannot rewrite everything in terms of trajectories. But actually, he was right. So in many-body, you transform complexity in trajectories. So all the informations about a many-body system are included in this time evolution between t and t prime. If you manage to describe exactly this evolution, you solve exactly the problem. And then how do you do it in practice? Well, in practice, you define two probabilities. One is to go from t to t prime, and the other to go from t prime to t. Well, this is needed because you cannot break the time reversal. So but you would see it by doing the math. You see that you need to include both probability to go back and forward in time. When you do it, you can actually build the Green's function that is a t-ordered product. Again, the need of this t-ordering, you say, wow, what did you tell you? I mean, how do you know that it's a t-ordering? Well, it is just a matter of doing the math. If you do the math of the single probability, psi dagger psi, you realize that at a certain point you do need to include an ordering. Otherwise, you cannot close the equation. Because the point is that, how do I calculate the equation of motion for this object? Oh, sorry, one important thing is that the Green's function actually, it is the key object of our, is the most elemental brick of the theory. In the heuristic approach, the response function was the most elemental brick. But if you go in many-body and you go still deeper in the theory, you realize that the Green's function is the most elemental brick in your theory. Why? Because it produces several observables. The density, the time-dependent density, it is just a contraction of the Green's function. So when you calculate the Green's function, or you have a theory for the Green's function, you have automatically a theory for the density. Automatically. So you see, for example, for this identity, a link with DFT. So, and then sometimes one says that many-body actually includes more than DFT. And it is actually due to this connection. From many-body, the core object of density functional theory, the density, is just a contraction. So with many body, it is just part of the informations I can get. Because if you leave the Green's function open, you have access to many more informations. So from this point of view, many body is more general than DFT. And indeed, if you do the expansion of the Green's function in exact n+1, n-1 states of the Hamiltonian, you can have the so-called Lehmann representation. So you can easily realize, this has been already introduced by Pedro, that the poles of the Green's function are the excitation energy of the system. So you have that the two terms of the Green's function have poles at the difference of excited energies of the system with n+1 minus n, n minus n, n minus 1. So Green's function is just, when it is exact, it gives access to the exact excitation energies. I mean, this is something that, okay, maybe I invite you to think about. So the many-body Hamiltonian is completely unsolvable. It is an horrible object. So it is a term that has a sum of single particle objects plus sum of 4 body. So, I mean, the electron-hole interaction will span 4 bodies. I mean, it's completely unsolvable, if not in super simple models. The power of many body is evident because it allows you to access the real excitation energies of a moisture Hamiltonian by a single body Green's function. So by just looking at the time evolution of one electron in the full many body, you have access to the excitation energy of the moisture. I mean, this is very powerful, extremely powerful. And actually, the many-body concept with Green's function is one of the concepts that is most widely used in physics. So you find it in high energy, in quantum field theory. So in the theories of particles, of leptons, and so on and so forth, Green's functions. You find it in the zero temperature many-body, the one we are doing now. If you increase the temperature, again, you have Green's function. If you do on the Keldysh contour, you have Green's functions. So Green's functions are really the most elemental bricks of, I would say, theoretical physics. Okay, then we need, say, if that's important, we need to find a way to calculate the equation of motion for these Green's functions. And then, now I just briefly show you a method to get equation of motions for any object appearing in Hamiltonian. In our Hamiltonian, our Hamiltonian is just a functional of these field operators. There are only electrons, but you can do theories even more complicated, where you have, besides those field operators of electrons, you can give me an Hamiltonian that is a functional of, I don't know, photons, whatever you want. If you are able to give me a field that describes that particle and an Hamiltonian, I can give you an equation of motion. How? Well, by using simple Heisenberg relation. So if you want, Schrödinger written for operators. So if you, you know that the time derivative of any operator appearing in Hamiltonian is given by the commutator of this object with the Hamiltonian. This is all we need. This holds for any field appearing in Hamiltonian. If it is a phonon, same. If it is a photon, same. Whatever. Then, if you have this relation, you can now, given this Hamiltonian, you can calculate easily the derivative, because you can apply the derivative to the Green's function. Why is this? I mean, this is simple. Okay, conceptually simple, then mathematically it can be not so simple, but okay, so stop. How do you do it? Okay, you know that E dt of psi RT is the commutator of psi RT the Hamiltonian. And then you know that the Green's function, G R T R prime T prime, is equal minus I, and then you have an average of the T product of C R T Psi dagger R prime T prime. Now, to calculate this commutator, you just need the commutation rules for the psi. So you know, I don't know, that's psi R T, sorry, anticommutator, psi dagger R prime R T prime, then R minus R prime plus minus I don't never remember, T minus T prime. So you know the basic computational or anti-computational relations depending whether it's a fermion or a boson. This is also for the electron field operators, for the boson field operator, whatever. So thanks to this, you can calculate explicitly this commutator. It is a long expression, but can be calculated. It's not super difficult, actually, because if it is a four-body operator, then whenever you do a commutation, you reduce a one field operator. This can be, I mean, it's really a textbook exercise. So once you are able to explicitly write this as a functional, this would be a functional of what? Of psi and of the column interaction. Thanks to this function, you can calculate the derivative of this object. Because if I do E dt of G, on the right-hand side, I have to do minus I E dt of this average. But then I have two terms. One is when it is inside. So T of E, dt psi RT, psi dagger R prime T prime. And then I have another piece that is just the derivative of the theta functions. This is not essential, it's a technical piece. But I mean, if you just, no complicated math. If you write on a piece of paper the definition of the Green's function, the definition of the Hamiltonian, anti-computational relations, and you do everything in a couple of pages, then you just get that to have the derivative of the Green's function, you have to do the T product of the derivative of the field operator. Now, this derivative can be obtained from the commutation, from the commutator. Now, if you do it, let's share screen. Yeah. Well, if you do it, you find yourself with this expression that the derivative contains this delta function. This delta function appears because of the derivative of the theta function. The derivative of the theta function is a delta function. So you can really see in practice how you get this. This is a very, I mean, an important step of the derivation because we understand where is the GW coming from. So you have this theta function, this delta function, then you have this G multiplied by H, and this also appears because of the commutator, and then you have this horrible thing. This horrible thing is a two-body Green's function. You see, psi dagger, psi, psi, psi dagger. So a two-particle Green's function. Okay, you say, oh, wow, this is terrible. How do I do it? Now we have two choices, actually, and there is actually a branch of physics that connected to each of the, you have actually three choices. And there are branches of physics connected to each of these choices. One is to continue with the hierarchy. So if now I want to calculate the equation of motion for L2, I need to do a step forward. I need to calculate the derivative with respect to T1 of this G2. And then you realize that this will induce a G3 with 3 bodies. And then you have 4 bodies, and so on and so forth. This is the hierarchy. It has also a name, now I don't remember, hierarchy. And there are ways of reducing this hierarchy. But there are also other ways. No, I don't like it anymore. OK, so we have 2 different steps to calculate this two-particle Green's function and to connect to this mass operator. So, yeah, this is a key step of the theory. Let's go back. So now you have E dt G proportional to G minus I, this horrible thing. What is the goal of your theory? Now you have to work to do what? You have to work to rewrite at the right-hand side this L2 in terms of G. So even if you want to pay the price of an integral differential equation or linear integral differential equation that eventually you can solve, you need to rewrite everything in terms of known objects. So the goal of both the Schwinger approach and the diagrammatic approach is to rewrite everything in terms of G. Everything in terms of G. Even if it is a complicated form, it must be written in terms of G. And Freeman-Dyson actually is the father of this expression, where you rewrite this complex object as the convolution of two objects. This is the self-energy. The self-energy is what remains out of the collision term in the equation of motion for the Green's function when you express explicitly the Green's function. It is a way to resum, to rewrite everything as a functional of the Green's function. So the formal derivation of the self-energy is by this identity. If you want, at this level, I can assume that there exists a form of the equation such that the two-body Green's function can be written by M by G. Now, there are two ways to do this, because, I mean, I don't have any other choice that work out this L2. And there are two ways. One is the Schwinger approach, and the other is the diagrammatic approach. The Schwinger approach is a way to rewrite exactly everything, but it's very similar to the FT in the concept, in the sense that in the FT, at a certain point you do the theory, very nice, you have Onenberg theorem, and then you have this exchange correlation function that you don't know. Then you derive Kohn-Sham. This functional produces a potential that you don't know. And you actually push what you don't know more and more inside, more and more further in the theory. So you say, I have Archie, and what is the remaining is the XC. But do you know XC? No, I don't know XC. So you actually rewrite everything exactly in terms of an unknown quantity. The Schwinger approach does the same. The role played by the VXC in many bodies is played by the vertex function. It is an object that is formally defined, but that you don't know. So you have to do approximations. The diagrammatic approach is much more dirty and elemental, because actually the aim is not to write everything exactly, absolutely not, but to understand what are the leading terms in this L2. What are the leading terms? So from a point, indeed, historically, the first one to be introduced was the diagrammatic approach. So immediately after the theories of many body by Wick, Feynman, and so on, and Bruckner, Law, the Gelman and Law theorem, and so on and so forth, the GW was introduced along with the T-matrix approximation using a diagrammatic approach based on physical concepts. And this is why I would like to introduce it to you, to give you an idea, also to have a different perspective. So let's take, for the moment, we can actually slow down for a second. Do you have questions? Are you lost? Or did you get at least the basic concept about this? No? What? Ah, yes. No, just to take a, with 2 minutes, then we actually it's a bit late. Did you get at least the physics of this? So a question that I could do you, very simple question. If now I tell you, apply GW on H2 molecule, what would you say? On a molecule composed by 5 atoms. So a colleague of you say, well, I am applying GW, I'm applying Yambo on H2 molecule. Would you say, yes, that's a good choice? Yeah, well done. Or?
It's a bad choice because there's no screening there.
Yes, 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 that's the point.
Archifog gives you kind of the same idea.
That's right. Yes, because when you are convinced that even if you don't know many-body theory, you don't know Schwinger, you don't know all this complicated stuff, you know that the main ingredient of GW is the dielectric function. If you have an isolated system, there is no screening. I mean, come on. It would better say to your colleague, I mean, don't spend time and computer resources to run GW, use Archifog. So this is important. I mean, also to understand the limitations and potential applications of the method. Don't just apply the method because all the people is applying the method. It's because there is a very nice Yambo Code. The developers are very nice persons. And the school was very interesting. We had good dinner and then everything. And then I apply GW because it's a waste of time. At the same time, if you are in a system where even if it is extended.
Sorry, Andrea, I'm Daniele.
Yes.
I don't want to be polemic, but just to say that there are hundreds of papers on GW on molecules.
Depends on the size, Daniele.
There are benchmarks about the recipes of GW for molecules.
Yes, but depends on the size.
What's your perspective on that? What's your thought about that?
Oh yes, but I said H2 molecule. H2. Of course, if the molecule has a number of electrons such to create plasmon waves or collective waves, then that's it. This is important.
Great.
I mean, the molecule has to be...
I heard 5 atoms, something like that. Totally agree about the
Oh,
H2.
5 atoms, so is enough. 5 atoms is enough to have collective excitations. Okay, so 2 atoms. The point is that, I mean, my message was just to get a physical intuition of the main ingredients of the theory that actually defines also the limits of the theory. At the same time, if you want to study a system where the main physical process is not driven by screening, but by other kind of processes, I don't know, short-range interactions, well, in that case, the self-energy is, the most proper self-energy is not the GW, but it's something else. I mean, for example, at the same time that GW was proposed, Galitsky proposed the so-called T-matrix approximation that actually is proven to be exact when you have a short-range interaction. So GW is really based on a dielectric concept. Okay, so in the last few minutes, if I have to decide between Feynman and Schwinger, I prefer Feynman because I like diagrams, so I prefer Feynman rather than Schwinger. Also because Schwinger is a single road. I mean, you don't have any other choice. You follow a strategy and you get to a point. I mean, it's an exact way of rewriting the problem. And my feeling is that actually makes appear more complicated. Instead, with the diagrammatic approach, you can use still, elemental concepts. So, how is the story? With the diagrammatic approach, actually, again, the main actor is the response function. And then with this, we conclude. Maybe I jump to the end to the last remarks about GW. So with the diagrammatic approach, actually, you really use a sort of Lego approach that you can even do with your kids. I mean, it's just a Lego. It's a way to connect stuff in order to create objects. So the response function, that is, again, the most elemental ingredient in the GW approximation, is a density-density response function. Now, you realize something that is actually at the basis of the... I mean, it is the reason why the Schwinger approach is so complicated and why the diagrammatic approach also has to be done with care. Now, the Coulomb interaction, yes, you see this object down here. This object down here. This is the beast, the problem of all the blah. It's the source of all problems. The column interaction is something that if you draw diagrammatically, is made like this. You see you have psi dagger, so you have R, R prime. Then you have, in R you have psi dagger, psi. So you have psi dagger, psi, R. In R prime you have psi dagger, psi. So you have psi dagger, psi. And here you have V. Now, this process is the elemental diagrammatic object. When you want to calculate a Green's function, the one needed to derive the mass operator, you actually have to do this very simple game. So you have that your Green's function is of the kind psi dagger psi. Sorry, psi psi dagger. So this means that I have a psi here and a psi dagger here. No, psi dagger. So now, you have to connect all the arrows in all possible ways, in such a way to not leave any arrow free, and also to not disconnect the diagram. I mean, it's a rule. I give you as a take it as a rule. So I can do several things. I can close like, let me go down, yeah. Simply to not do the crossing. I can do like this, and I can do this. I mean, simple. I mean, your kid my kid could do the same. And this is archery. This is just archery. This diagram, this closing is archery. And the point is that this V actually appears not just once, but an infinite number of times. All the problem is due to this interaction, actually, in the dynamics, appears an infinite number of times. So if you write in terms of a sum. So now, the point is, how do I choose the way, if you have already two of this, if you have already two of this, you have already lots of possibilities to how to connect it, right? I mean, there are actually at the order 2, there are 2 factorial. So it is 6 terms. There were different ways to connect it. And if you go to high orders, you have more. How do you select the diagrams? Well, the diagrams are selected in the GW approximation. If you go on many body textbooks about GW, you see that the GW approximation is introduced just for one specific reason, that is connected to the dielectric approximation. You can realize easily that if you consider diagrams like this, where you see when the connection here is done in such a way to just do this way. This is the lowest order diagram of GW, and as this form. Now, the column interaction, 1 over R minus prime, has the problem that when you do the Fourier transformation, it goes like 1 over Q squared. So the Fourier transform of V is 4 pi divided by Q squared. Q squared, it diverges. So in homogeneous electron gas, you can prove on a piece of paper that the lowest bubble diagram is divergent. I'm almost done. Is divergent. So the GW approximation is a way to cure this divergence, and is the only way to resum diagrams in such a way that this divergence is regularized. This is the GW approximation. And then you can prove on a piece of paper that if you just consider all diagrams of this form for the interaction, so the V, the bare interaction is replaced by 1 bubble, 2 bubbles, and so on and so forth, you get that this interaction goes like this. V of W, V of Q, instead of going like 1 over Q squared diverging, it gets this difference. Chi enters in the definition of W. Now, this W of Q is not divergent anymore. So if you consider just the diagrams where you have an arbitrary number of bubbles, it can be proved on a piece of paper that this series is regular in Q, so it does not diverge. if you do this, you get GW, because GW is just the all possible diagrams where you have different bubbles there inside. Now you may wonder, when is it exact? Can you tell me when is it exact? Surely it is the only way, when you have long-range interaction, is the only way to treat this divergence. On the other hand, it can be proved that in the high density limit, it gets exact. When you have an homogeneous electron gas with high density of electrons, then GW becomes the dominant diagram. Clearly, all the real materials are in the middle. They are not either with high density or low density. But this gives you an idea of the physical content of the GW approximation. Then all these diagrams are summed together, and then you get, no, so I'm going, yes. All the bubbles define actually the screen interaction, and the screen interaction that is defined in this way should give you the, it's there, so it's the GW. So W is just introduced as the sum of bubbles that cures the divergence of the long-range column interaction. So now you have different puzzles of the story, right? So you know that GW is very much connected to the electric properties. In addition, when you have an homogeneous electron gas with the long-range interaction, this dielectric picture is the only one able to fix the divergence. So it's the only physical one. So in a way, the GW is the leading term in a system with the electric properties and with a long-range interaction. Is the leading term. Okay, so of course, I don't have problem to introduce the Schwinger approach. So the Schwinger approach actually rewrites everything exactly. I mean, this is a way of rewriting everything exactly, introducing more terms. Behind the response function that is pi, p, and w, you have also this vertex. But it's just a way to push in something, in some definition, the unknown part of the story. So I just conclude with, actually, at the end of the story, what is GW doing? So the role of GW is to describe correlation, and will just lead to an effect that, in general, is opposite to Hartree-Fock. So the Hartree-Fock gap correction will tend to increase the gap, and GW will reduce the gap. Now, a simple question, but I want a quick answer. As the GW is the screen Hartree-Fock, do you expect that in modulus the Hartree-Fock correction to be larger or smaller than the GW correction? I mean, GW is the screened Hartree-Fock. Do you expect the GW correction to be larger or smaller than the Hartree-Fock gap correction? Yes, smaller. Good. Yes, yes. It is smaller. And actually, when you go to the beta-salpeter effects, it gets even more tiny. But physically, the trend is to open Hartree-Fock, close. Okay, then in general, GW, that is Hartree-Fock plus correlation, gives a reasonable agreement with the gaps. Then, of course, this is just a picture to close the talk, because otherwise, if I show you cases where it doesn't work, it would be, we would open, I would give you dubs. Well, I don't have to give you dubs. I have to give, say, clear messages. It's going to work. So in general, in general, it works. But of course, whenever you have systems where there is something that works against the dielectric properties, then in those cases, you may expect GW to be less efficient. For example, transition metals, where you have localized orbitals, that they produce in the material a combination of extended over localized properties. So there are different length scales. In that case, GW has problems. It can have or even lots of problems. Okay, and then some references. There are many. The GW has been reviewed. There are reviews about GW, so the theory can be really found anywhere. And after so many years, it has been applied so many times that it is reasonably valid theory. And Thank you.
Thank you, Andrea. And the session is open for questions, if you have any.
Too much. Oh, sorry, too much. And I didn't do Schwinger. I mean, of course, this is kind of things to teach in a course, not in 1 hour. I understand.
So maybe I can start with a question. So you have stressed a lot the importance of screening. So one other aspect of GW is that it has a dynamical self-energy, so it's a dynamical screening. Can you comment about the dynamical part?
Yes. So you will see it in practice. You will see in practice in the hands-on. It was written somewhere. Oh, did I remove it? No. Oh, fuck. Yes. So the frequency dependent of the self-energy is a clear manifestation of the quantistic properties of the theory. So you need an analogy. You did an analogy. So when you do Ashifo, you have your Hamiltonian that contains an independent particle part plus an interaction part. So Hamiltonian interaction, electron-electron. Now, this complex thing in Archifoc is replaced by H plus H Archifoc plus V Archifoc. So it is single particle. This is two bodies. This is one body. This is all one body. So the idea of Archifoc is to replace the full interaction with a mean field potential. With many body, the picture is similar but contains a very drastic difference. With many body, approximatively, you can do the same trick where you have H, but you have a frequency or a time-dependent potential. So many body rewrites everything in terms not of a static potential, but a time-dependent potential. The reason is that there is retardation. There is a very quantistic object. So if you write everything in terms of dynamics of the electrons, you have to consider that during the trajectory, the electrons will see the time evolution of the system around. So the density oscillations will see the system oscillating in time, and so on and so forth. This time dependence actually is reflected in the solution of the problem in a picture like this. So if you have here, imagine for the emission spectra, you have the energy. In the independent particle picture, you have a delta function. Let's call it this E naught. Within Archifoc, you have a change of the energy, still delta function, well-defined energy. When you introduce the self-energy, actually this thing gets shifted, broadening, and eventually structures. This is, of course, magnified. So physically, the frequency dependent is reflected in the broadening of the line and also in the appearance of structures besides the main peak. So this is the coherent and incoherent part of the Green's function. So here you can have plasmon replica or phonon replica or whatever. So the frequency dependent physically is describing the fact that the dressed electron, so coherent with the Landau picture, is not a full charge object, but contains just a fraction of the charge and eventually also non-coherent parts. So the quasi-particle picture is richer than the single particle picture in an emission approach like Archifoc or DFT.
Okay, so we have one more question here and then one from the audience online.
So my question is, how do you quantify these the screening, does it mean that as the number of particles grows, the screening also grow?
How do you quantify the screening?
Yes, exactly. So what's the limit? And is there any possibility to over-screen and also to under-screen the system?
Okay, the screening, okay, it depends on your system, of course. In general, as Daniele was mentioning, the screening appears also in reasonably tiny molecules. So whenever you have enough number of electrons to collectively react, then you have the electric properties that are not irrelevant. How do you do it? How do you understand specifically to your system? Well, one thing you can do is to calculate the electric properties at the beginning and to see if you have any difference between, if you can define the yields. The yields compared to the absorption involves collective excitation. So if you look at silicon, for example, you ask Yambo to calculate absorption and yields, you will see they are completely different. Davide mentioned it yesterday. Epsilon absorption is in the lowest energy range, while the yields has a very clean big plasmon at 20 V. If you see that those two things get very near each other, and you see the disappearance between the difference of absorption and yields, then you may wonder, this system cannot create plasmons. In that case, GW is at risk. Still, it's not said that it won't work, but surely the system will want to have clear and sharp dielectric properties to motivate from the Ab-initio the GW approximation.
Okay, then I see a question online from Burak Özdemir. Can you try to unmute yourself?
Hello.
Hello.
In the materials project website, I tried a couple of materials with calculation with GW and found gaps that are significantly lower than GGA gaps. I didn't have the chance to compare to experiment, but what should I think? Is something going wrong? Is the GW gap worse than the GGA gap, or what are your comments about this?
So can you give an example of the materials where you were seeing that?
He said at the beginning, but he didn't get it.
I really don't remember the chemical constituents.
Well, in general, it should be tinier then. So in general, you should get a GW gap that is smaller. That is bigger than, sorry, it is bigger than the GGA. You got smaller instead.
Yeah,
I found that it was smaller. GGA gap was smaller than GW gap was smaller than GGA, and I'm curious which one is more reliable in that case.
Well, I would say that in general, GW is more reliable than GGA for many reasons, but then usually it opens the gap. So.
Well, what you can do, what I would do personally if I had a problem, is to, I don't know which code you use to do GGA, but if it is quantum espresso, you can calculate Hartree-Fock. So I would calculate Hartree-Fock with quantum espresso and with Yambo on top of GGA to see to what extent they are completely different. Because it is, I mean, the reason why the gap of GW is larger than the DFT one is the DFT one is that in DFT, correlation and exchange are treated in approximative way, and the cancellation, and it works because of cancellation, but this cancellation is not complete. But the two components, exchange and correlation, has to be in equilibrium, sort of. If you have a very large Hartree-Fock correction or a very tiny Hartree-Fock correction, then this cancellation may be at risk. This depends on the system. In general, for many systems, the order of magnitude between exchange and correlation allows you to say that the gap is larger. But it depends. I would check the correctness of your Hartree-Fock calculation and eventually the quality of the orbitals you're using to do GW.
Okay, thank you.
Andrea?
Yes?
Andrea, I think that it is important to specify when talking about the DFT gap, if you mean difference of Kohn-Sham eigenvalues or difference of total energy with different number of electrons, because the two are very different.
Yes, absolutely. I mean, the DFT gap we are talking about is the one more easy accessible by calculations. When you do a calculation with quantum espresso or Ab-initio or whatever, VASP, from the report, you see immediately the gap within Kohn-Sham. This gap is smaller than the through DFT gap in the sense the one calculated in terms of total energy differences.
Yeah.
Okay, just time for one last question from the audience. Ah, okay. There is.
So from the equation, is it like the self-energy is a better approximation for the exchange correlation from the equation which I'm seeing? Is it like a better approximation for the exchange correlation?
Yes, it is.
Okay, so if you
remember, the exchange and correlation potential in DFT is just a way needed to get the exact total energy and exact density. It's not meant to give the right gap.
Okay,
so it's a different, even if they are both exchange correlation, something they are very different in nature.
So if you have like a homogeneous electron gas where LDA can give us like a exact exchange correlation, so then do we, I mean, is the self-energy equals to the exchange, the VXC here?
No. There is this is an important thing you have to keep in mind. So given the Hamiltonian, given the same Hamiltonian, with DFT you get the exact density and exact total energy dot as a function of the exact density. This, if you have the exact potential, fine. Then you saw from the Lemon representation, well, and instead many body can give you the exact excitation energies. So with a single calculation, with many body, you do single calculation, Green's function, you get the excitation energies. This was written in the Lemon representation. This is proven in Lemon. Now, can DFT access the same thing? Well, you have to do two calculations. So you do one calculation with, actually, in this case, you should specify the number of electrons. So you should do a calculations with n electrons, and then a calculation with n plus minus 1. Okay? Once you do those two calculations, you can do the differences. And then you can compare the total energy difference within the FT with the ones from many body. If the potential is exact, those differences are the same. If the potential is exact, then you may wonder now, oh, but then you talked about this coherent, non-coherent, blah, blah, blah. So how would this fit with the representation where the excitation energies are real and exact in the two approaches? This is because this is not the excitation energy. This is the spectral function of the single particle. So Lemma representation gives the components of this thing. So this means that given the exact potential, you get exactly the same exact self-energy, exactly the same excitation energies. But even if you have the exact, you use only the n electrons calculation to calculate the E Kohn-Sham. What is the HOMO is the upper or lower? Okay. LUMO minus E Kohn-Sham HOMO. This is different from the gap you get here, because this lacks of the effect of adding one electron. When in DFT you add one electron, you realize that the Kohn-Sham problem gets a correction. This is the functional derivative. Then, sorry, the derivative discontinuity. Not the functional derivative. The derivative discontinuity is a correction to the Kohn-Sham of the problem with n electrons because you add one electron. So when you calculate with quantum espresso the gap of Kohn-Sham or material, you miss a piece. If you want to calculate exactly within that flavor of DFT, that can be LDA, GGA, whatever, you have to do two calculations by adding and removing one electron. In that case, you have access to the same excitation energies. This is an essential difference. It's really important that you get it. Otherwise, you may wonder, oh, why the gap of GW is different from the one of DFT? If I get the exact potential, do I get the exact gap? No.
So is it the derivative discontinuity is always positive, or
It is, well, always, I wouldn't say always. In most of the cases, it is positive, yes. Always is a big word. I mean, I don't know if always. What? For LDA, it's 0, right? Yes, because the LDA, the exchange correlation potential is an analytical function of the density. That's right. You are right.
then the gap should be equal to the difference?
No. No, LDA is an approximation, it's not exact. It's not expression. I mean, LDA is an expression, is an approximation that is actually, you could say, it's so bad that it produces a 0 derivative discontinuity. And actually, most of the reason why LDA works is because the exchange and correlation, they cancel each other. But there are materials, I think I work on that. Yes, I work on that. There are materials where actually it doesn't bind. If there is a mismatch between exchange and correlation, LDA doesn't work. So LDA is not exact. If you prove me that the exact potential is an analytic function of the density, then you're right. The derivative discontinuity is non-zero. But this has not been proved. Actually, it has been proved the other way around, that the exact density, the exact potential is discontinuous. The derivative is discontinuous in the number of electrons. This has been proved. There is a theorem.
Okay, I think it's time to move to the next lecture. So we thank Andrea again.